So the last video on Gauss law itself became of 1 hour. So since dipole is an important topic and every year question comes from dipole in NEET, I am taking this hour separately. So talking about the dipole in this hour. But why do we have to study dipole separately? What makes it so special? Let's see. First of all, what is a dipole? Sir, a pair of equal and opposite charges separated by some distance constitute a dipole. A pair of two equal and opposite charges separated by some distance constitute a dipole. So if you have got a charge of minus q and plus q separated by some distance, a pair of equal and opposite charges separated by some distance, they constitute a dipole. But why is dipole so special? Because of two reasons. The first reason, in the real world, everything is made up of molecules. And molecules have some dipole moment associated with them. For example, if you have got an HCl molecule, since chlorine is more electronegative than hydrogen, it pulls the electron cloud of hydrogen towards it. So chlorine gets partial negative charge while hydrogen gets partial positive charge. From the principle of conservation of charge, the magnitude of negative charge that chlorine gets is same as the magnitude of positive charge that hydrogen gets, because initially both of them were neutral. So what you have here is a pair of equal and opposite charge separated by some distance. Another important thing about dipole is that when we were talking about null point, I said that we can find null point for like charges, we can find null point for unlike charges. Here we have got unlike charges, so I will talk about unlike charges. If I have got a positive charge and a negative charge, then I said that the null point, the zero electric field point, is found on the line joining the charges, outside the charges, closer to the charge of smaller magnitude. But here both the charges have same magnitude. So where do you find the null point? The answer is nowhere. You can't find a single point in space where the electric field due to dipole is zero. So sir, if you have a pair of positive and negative charge, there is no point in the entire space where the electric field due to the system of these two charges will be zero. No. So at every point in space, they will produce a net electric field. Yes. That's the second important point about dipole. Now we define a quantity which is called dipole moment. Dipole moment, represented by the symbol P, is a vector quantity. Maths is the language of physics. So we say that the dipole moment vector is a vector quantity, and the dipole moment vector is equal to the magnitude of charge times the position vector of positive charge with respect to negative charge. The magnitude of charge times the position vector of positive charge with respect to negative charge. So you have to draw a vector from the negative charge to the positive charge. Here again, between physics and chemistry, there is a problem in the sign convention. In physics, we take the direction of dipole moment from negative charge towards positive charge. And in chemistry, we take the direction of dipole moment from positive charge towards the negative charge. But here we are talking about physics. So just remember that a physicist moves towards positivity in life. So a physicist moves towards the positive charge. So in physics, when you are writing dipole moment, you take the magnitude of charge times the position vector of positive charge with respect to negative charge. So what is R? The position vector of positive charge with respect to negative charge. A physicist moves towards positivity in life, from negative charge towards the positive charge. So keep this particular thing in mind. So dipole moment is a vector quantity. It is equal to charge times the position vector of positive charge with respect to negative charge. So let's see one small example based on this. Two charges of 2 coulomb and minus 2 coulomb are placed at 2, 3, 0 and 3, 1, 2. Find the dipole moment. Dipole moment is which type of quantity? Vector quantity. Now you have got two charges of 2 coulomb and minus 2 coulomb placed at this point and this point, and you need to find the dipole moment. What to do? So simply the dipole moment is the magnitude of charge, which is here 2, times the position vector of positive charge with respect to negative charge. And to find the position vector of positive charge with respect to negative charge, all you have to do is position of positive charge minus position of negative charge. Just like velocity of 2 with respect to 1 is v2 minus v1, position of 2 with respect to 1 is position of 2 minus position of 1. So position vector of positive charge with respect to negative charge will be nothing but position of positive charge minus the position of negative charge. So you will say the dipole moment vector will be equals to magnitude of charge times the position of positive charge with respect to negative charge. So magnitude of charge 2 times the position of positive charge with respect to negative charge, that will be position of positive charge minus the position of negative charge. The position of positive charge will be written as 2i cap plus 3j cap plus 0k cap, and the position vector of negative charge will be written as 3i cap plus j cap plus 2k cap. So when you substitute it, you get 2 times position vector of positive charge with respect to negative charge. So position vector of positive minus the position vector of negative, you get 2i cap minus 3i cap, that becomes minus i cap. 3j cap minus j cap, that becomes 2j cap, and 0k cap minus 2k cap gives you minus 2k cap. So what you get here is 2 times of minus I cap plus 2j cap minus 2k cap. Just multiply 2 with each term, you will get the dipole moment vector to be equals to minus 2i cap plus 4j cap minus 4k cap. Simple. So dipole moment is a vector quantity. The direction of dipole moment is from negative charge towards the positive charge. Let's move on. How do we write the field due to a dipole? So if you have got a positive charge and a negative charge separated by some distance, I have just told you that you can't find a single point in the entire space at which the electric field due to this system of charge is 0. Now, how to find the electric field due to this system of charge at a point on its axis? Now, if we need to find the electric field at an axial point, the first thing we need to understand what is the direction of electric field on the axis of a dipole. So think that you have a positive charge, yeah, you have a negative charge, yes. What will be the direction of dipole moment? Sir, from negative charge towards positive charge. This will be the direction of dipole moment. Now think of electric field lines due to the system of this positive and negative charge. So sir, electric field line will come out of positive and they will terminate into negative, right? I am talking here on the axis, okay? So at all these points, the electric field line will be away. Why, sir? See, if you have got a positive charge and negative charge, and I ask you, determine the direction of electric field at point A. So you will say the positive charge will produce a field away from it. The negative charge will produce a field towards it. But since the positive charge is closer, the net electric field at point A will be towards left. If I ask you about a point on the right of this dipole, at this point, the direction of field due to negative charge will be towards it. The direction of field due to positive charge will be away from it. But since the negative charge is closer, the strength of the field due to negative charge, which is towards left, will be higher. So the net electric field will be towards left. So at a point on the left of this dipole, the field is towards left. At a point on the right of this dipole, the field is towards left. So we say that the direction of field due to a dipole on its axis is in the direction of dipole moment. So if you have got this negative charge and positive charge, the direction of dipole moment is from negative to positive. Yes, sir. At a point on the axis, whether here or whether here, at point X or at point Y, the direction of electric field due to the dipole on its axis is same as that of dipole moment. So at both these points on the axis, the direction of electric field is same as that of dipole moment. Sir, but what if I need to write the direction of electric field between the charges? I said in the very beginning, why are we learning dipole? Because molecules have got dipole moment. Now, if you have got an Axial molecule, what's the point of understanding the electric field due to a single Axial molecule at a point between them? You need to understand that we are looking at the electric field produced by an Axial molecule at an outside point rather than in between them. So when I say that Because of a dipole, the electric field produced by it on its axis is in the direction of dipole moment. I'm talking about the outside points. I'm not at all talking about the points between the charges. Definitely at the point between the charges, let's say this point, the field due to negative charge will be towards it, the field due to positive charge will be away from it. So both the field will be in same direction, and that will be in direction opposite to the dipole moment, which is from negative charge to positive charge. So sir, when we are talking about the electric field due to dipole on the axis, we are talking about the points outside the charges. Yes. On the line joining the charges. Yes. Now, everywhere I want to draw minus q plus q. It's my personal habit that I just draw an arrow. When I draw an arrow to represent the dipole, it's your understanding that you will understand that this tail represents the negative charge and the head represents the positive charge, because the direction of dipole moment is from negative charge towards the positive charge. So if we need to write the electric field at an axial point, and let's say the separation between the two charges is A, and the distance at which we need to write the electric field, that distance from the center of dipole is R. So you will say, sir, at this point, due to the positive charge, the field will be away and it will have higher magnitude because the positive charge is closer. Yes. Due to the negative charge, the field will be towards it, but it will be weaker because the distance between the negative charge and this point is higher. So how will you write the net electric field at this point? You will say that the net electric field at this point will be equals to electric field due to positive charge minus the electric field due to negative charge. So the direction of field at this point is same as that of dipole moment from negative charge towards positive charge. You get the same direction of field on the axis. Now the electric field will have magnitude equals to the field due to positive charge minus the field due to negative charge. The field due to positive charge will be K into Q upon the separation between positive charge and this point whole square. Now the distance of this point from the center of dipole is R and the length of dipole is A. So the distance of this point from the positive charge will be R minus A by 2. So this distance will be R minus A by 2. While the distance of the same point from the negative charge will be R plus A by 2. So you will say the net electric field at this point will be the field due to positive charge, which is kq upon r minus a by 2 whole square towards right, minus kq upon r plus a by 2 whole square towards left. So when you take kq common, you get kq into 1 upon r minus a by 2 whole square minus 1 upon r plus a by 2 whole square. Now you can cross multiply these things, and when you multiply the denominator, you will get r square minus a by 2 whole square whole square. So that becomes kq into, this goes up, r plus a by 2 whole square minus r minus a by 2 whole square upon r minus a by 2 whole square into r plus a by 2 whole square. So that becomes r square minus a square by 4 whole square, or r square minus a by 2 whole square whole square. Now when you open up this term, r plus a by 2 whole square, you get r square plus a square by 4 plus 2 into r into a by 2, that becomes ra. And when you open up this one, you get r square plus a square by 4 minus 2 into r into a by 2, that is minus ra. So when you open up the second bracket, the minus get cancelled. So here you have got ra, here you have got minus of minus ra, that again becomes ra. So when you do the calculation here, becomes RA minus RA, that becomes in numerator 2RA. So you get KQ into 2RA upon R square minus A square by 4 whole square. So you get the net electric field equals to KQ into 2RA upon R square minus A square by 4 whole square. You can club this Q and A and write it as the dipole moment. What you get is 2 K, in place of Q and A, you can write P, the dipole moment, into R upon R square minus A square by 4 whole square. So the net electric field at a point on the axis comes out to be 2 kpr upon R square minus A square by 4 whole square. This is the formula. So do we need to remember this? If you can't derive it within 20 seconds, then you need to remember it. What I recommend is solve it twice with your own hand, reach this solution within 20 seconds, and then chill in life. You do not need to remember this ugly looking formula. But the type of dipoles we have got interest in are short dipoles. Why? Because sir, in HCl molecule, the separation between H and Cl is small. So when we are talking about short dipoles, this length A is really small. So if A is less than R, if your dipole is short, this means that the separation between the charges is small. Then you can neglect this term of A square by 4 in front of R square. So what you get is 2kpr upon R square whole square. So that becomes 2kp by R cube. There is R raised to the power of 4 in denominator, that becomes 2kp by R cube. So you need to remember this particular formula, that due to a short dipole of dipole moment P, at a distance r on its axis, the electric field is in the same direction as that of dipole moment, and this electric field strength is nothing but 2kp by R cube. Now since the direction of electric field and dipole moment is same, we can even write this electric field in vector form as the electric field vector on the axis equals to 2k times dipole moment vector on the axis upon R cube. Why? Because the direction of electric field and the dipole moment is same for an axial point. Now how to write the electric field due to a dipole on an equatorial point? So what is an equatorial point? So if you have got charge minus q and plus q, and this is the line joining them, think of the perpendicular bisector. Any point on the perpendicular bisector is called an equatorial point. It is at same distance from both the charges. So if we have got these two charges, negative and positive, and let's say there is one point here at distance r from the center of dipole, center of the line joining these two charges, we know that the negative charge will produce an electric field towards itself, let's say of strength E, and the positive charge will produce the electric field of same strength but away from it. Now bachcho, let's say this angle is theta, so this angle will also be theta. So we can say if we have got these two electric field vectors E and E such that this angle is theta and theta, what will be the resultant? We can break down these two electric field vectors as E sin theta, E cos theta, as E sin theta, E cos theta. We can cancel out E cos theta, and the net electric field will be 2E sin theta. So visualize the point on the equatorial line, and because of the negative charge, the field will be towards it. Because of positive charge, the field will be away from it. Let's say this distance from the center of dipole is r, and the distance of one of the charge from this point is d. So we will say that if this angle is theta, the net electric field is 2E sin theta. How do we write E and sin theta? We will say that E is nothing but the field due to one of the charge q at distance d. So E has to be equals to kq by d square. And how to write sin theta? Look into this right angle triangle. You know that this distance is a by 2, right? This half distance is a by 2. This distance is r. So this distance d has to be equals to under root of a by 2 whole square plus r square, right? But let's call it d. So you can say sin theta has to be perpendicular upon hypotenuse. So sin theta will be equals to a by 2 upon d. So that becomes a by 2d. This will be the value of sin theta, where d will be under root of r square plus a by 2 whole square, and sin theta will be equals to a by 2 upon d. Now substituting the value of E and sin theta, we will get that the net electric field will be equals to 2 into kq upon d square multiplied by a by 2d. So that 2 and 2 get cancelled. In place of q into a, you can write the dipole moment p, and here d square into d gives you dq. So that will be kp by dq. So the strength of electric field is the Coulomb's constant times the magnitude of dipole moment upon d whole cube. What is d? Under root of r by 2 plus a by 2 whole square. So substitute the value of d. This root can be thought of as raised to the power of half. So if you have got x root whole cube, can you write it as x raised to the power of half whole cube, and that can be written as x raised to the power of 3 by 2. So here you can write the same thing as kp upon r square plus a by 2 whole square raised to the power of 3 by 2. So this is something you need to remember if you can't reach this point within 20 seconds. What I recommend students personally is do it twice with your own hand and try to reach this point within 20 seconds. It's not a difficult derivation. You just have to write the value of E, the value of sine theta, and you need to understand that D has to be equals to under root of R square plus A by 2 whole square. Practice it twice with your own hand. That will keep you tension free on your judgment day. You won't have to mug up a stupid formula which is ugly looking. So now we know that the net electric field at an equatorial point came out to be kp upon r square plus a by 2 whole square raised to the power of 3 by 2. But the type of dipole we are interested in are short dipoles. Now, for a less than r, you can neglect this term in front of r. So what you will get is kp upon r square raised to the power of 3 by 2, and r square raised to the power of 3 by 2 will be nothing but kp upon r cube. So E net comes out to be kp by r cube for a short dipole. For a dipole in the case of which the separation between the charges is way smaller than the distance of the equatorial point from the center of dipole. Now here we can write even the electric field in the vector form. If you have got this short dipole here, so this is the negative charge, yes. This is the positive charge, yes. Think of an equatorial point, let's say this. The field due to negative charge is towards it. The field due to positive charge is away from it. We got the net electric field in direction of dipole or in direction opposite to the dipole. So remember that at an equatorial point, the direction of electric field because of dipole is in the direction opposite to the dipole moment. Or you can simply think that, bachon, if you have got a negative charge and a positive charge, same magnitude. So field lines originate at negative and terminate at positive. At any point on the equatorial line, the direction of field due to this dipole is here, right? Think of tangents. Okay. Now, the direction of dipole moment is from negative charge to positive charge. The direction of field is opposite to it. So at an equatorial point, the direction of field is opposite to the direction of dipole moment. So in the vector form, we write the electric field at an equatorial point to be minus kp by r cube. Sir, why a minus sign? Because the direction of electric field is opposite to the direction of dipole moment. Because the direction of electric field is opposite to the direction of dipole moment. Now we need to understand how to write the electric field due to a dipole at a random point. Let's say we have got this dipole of dipole moment P, and we need to write the electric field at a random point whose distance from the center of dipole is r and whose position vector makes an angle theta with the direction of dipole. To answer it, just remember that if you have a dipole of dipole moment P, then at an axial point at distance r, the strength of electric field is given by 2 kp by r cube, and the direction of electric field is same as that of dipole moment. While at an equatorial point at distance r, the direction of electric field is opposite to that of dipole, and the strength of electric field is equals to kp by r cube. So how to find the strength of electric field due to this dipole of dipole moment P at a distance r from its center? Dipole moment is a vector quantity. So you can break down this dipole moment vector P into component in the direction of the position vector of the point. This will be P cos theta. And in the direction perpendicular to it, this will be P sin theta. So rather than thinking of a single dipole moment P, you can think of two dipole moments P cos theta and P sin theta. So do this. Now for this P cos theta, this point at distance r is your axial point. While for P sin theta, this point is equatorial point. So you will say because of P cos theta, at this point, there will be an electric field in the direction of dipole, and this electric field will be 2k into P cos theta upon r cube, as the strength of dipole moment is P cos theta. While because of P sin theta, for which this point is an equatorial point, the direction of electric field will be opposite to the dipole moment, and the strength will be Kp by r cube, where the magnitude of dipole moment should be substituted as P sin theta. So you get Kp sin theta by r cube. So visualize the electric field due to this P cos theta. For this P cos theta, this is axial point. So the strength of electric field will be K into P cos theta into 2 by r cube. And because of P sin theta, the strength of electric field will be Kp sin theta by r cube. Now the net electric field at this point due to this dipole will be the resultant of these two electric fields. So just visualize these two electric fields. So you will say the electric field making an angle theta with the direction parallel to the dipole moment, which is due to the component P cos theta, is 2 Kp cos theta by r cube, while the electric field which is due to the component P sin theta, for which this point is equatorial point, is Kp sin theta by r cube. The resultant of these two electric field will give you the net electric field, and let's say this net electric field makes some angle phi. So you can say that this net electric field will be the resultant of 2 Kp cos theta by r cube and Kp sin theta by r cube. So you will get the net electric field is under root of Kp sin theta by r cube whole square plus 2 Kp cos theta by r cube whole square. So here you will get Kp by r cube common. Once you take it outside, you get Kp by r cube times under root of sin square theta plus 2 square gives you 4 cos square theta. Now even you can write bachcho that tan phi has to be equals to Kp sin theta by r cube upon 2 Kp cos theta by r cube. 2 Kp cos theta by r cube. So bachcho cancel out Kp r cube r cube. So what you get is tan phi equals to tan theta by 2. Tan phi equals to tan theta by 2. Remember this particular result, tan phi equals to tan theta by 2. Now we can write E net as Kp by r cube into under root of 1 plus 3 cos square theta. Sir, how do you get it? Easy. We have just written E net equals to Kp by r cube into under root of sin square theta plus 4 cos square theta. Think of this 4 cos square theta as sin square theta plus cos square theta plus 3 cos square theta. And this sin square theta plus cos square theta becomes 1. So you get 1 plus 3 cos square theta. So the net electric field will be Kp upon r cube into under root of 1 plus 3 cos square theta. And this net electric field makes an angle theta plus phi with the direction of dipole moment, where we know that tan phi comes out to be equals to tan theta by 2. Sir, how? See, angle made by the net electric field with the direction of dipole moment is theta plus phi, where tan phi will be equals to this component Kp sin theta by r cube upon this component which is 2 Kp cos theta by r cube. So this Kp r cube get cancelled. What you get is tan theta by 2. So tan phi equals to tan theta by 2. This is something you need to remember. So the net electric field is Kp by r cube under root of 1 plus 3 cos square theta, and the angle made by the net electric field with the direction of dipole is theta plus phi, where tan phi equals to tan theta by 2, or the net angle is theta plus tan inverse tan theta by 2. Why? Because from this correlation we can say phi equals to tan inverse of tan theta by 2. Okay. So a question here. If the field at a point P on the axis of a short dipole has a magnitude E. If the field at a point P on the axis of a short dipole has a magnitude E. If the dipole is turned by 90 degree, what will be the field strength at the same point? So if you have a dipole of dipole moment P here, and at a point on its axis, the electric field strength is E. If you turn the dipole by 90 degree, this is the new orientation, that this same point, which was for original dipole an axial point, for the new dipole, this same point will be an equatorial point, right? So think of the before and after condition. So initially, you are talking about a point at distance r on the axis of dipole. Once you turn the dipole by 90 degree, now same point is on the equatorial line at distance r. So for an axial point, we know that the electric field strength is 2 kp by r cube. But at the same distance on the equatorial line, the electric field strength is kp by r cube. Hence, the strength of electric field vector becomes half. So the magnitude of electric field at same distance on the equatorial line is half. So the magnitude of field becomes half. So if the original field was E, the new field will have a strength equals to E by 2, because at same distance on the equatorial line, the strength of electric field is half. Moving on. Determine the value of theta so that the field produced by the short dipole is perpendicular to the direction of dipole moment. So you have got a short dipole. They are asking what has to be the value of theta so that the electric field E net produced by the short dipole is perpendicular to the direction of dipole moment. For the net electric field produced by the short dipole to be perpendicular to the direction of dipole moment, theta plus phi has to be equals to 90 degree. And we know that tan phi equals to tan theta by 2. So since we know that tan phi equals to tan theta by 2, and now in place of phi we can write 90 minus theta. So we get tan of 90 minus theta equals to tan theta by 2. Tan of 90 minus theta can be written as cot theta. So cot theta equals to tan theta by 2. Cot theta can be written as 1 by tan theta. So 1 by tan theta equals to tan theta by 2. Bring this tan theta up here, this 2 here. So what you get is tan square theta equals to 2. Once you know that tan square theta has to be 2, this means that tan theta has to be root 2. Hence, tan theta has to be root 2 for the electric field at this point to be perpendicular to the direction of dipole. Moving on. How to write the potential at a point due to a short dipole? So visualize a short dipole and think of a point whose distance from the center of dipole is r and whose position makes an angle theta with the direction of dipole moment. Now for this particular position of point where you need to write the potential, you can see that the distance from the positive charge is less while the distance from the negative charge is more. Hence at this point the net potential has to be positive because it is closer to positive charge. Now how to write the net potential at this point? To make you understand, rather than thinking of a short dipole, I am drawing a little bigger dipole. So think that you have got this charge minus q plus q, and there is some random point in space whose distance from the center of dipole is r, and the position vector makes an angle theta with the direction of dipole moment. Now I am drawing it big, but think that the dipole is short, so the value of a compared to the value of r is small. Now the distance of two charges will be different. Now how can you write this distance in terms of a, r and theta, and how can you write this distance in terms of a, r and theta? Now beta, do understand these lengths are nearly equal, right? Because we are talking about a short dipole, but still there is some difference in the length. How to find? So you will say, if I drop a perpendicular here, if the central line length is r, then this longer line length, the distance from the negative charge, is greater by this much of distance. How to get this much of distance? So drop a perpendicular. If this angle is theta, this angle will also be theta. This length will be a by 2. So this length has to be a by 2 cos theta, extra length. So you will say if the center line distance is r, then this negative charge distance will be greater by some amount, and this amount will be nothing but a by 2 cos theta. So this distance from the negative charge comes out to be r plus a by 2 cos theta. Similarly, you can see that the distance from the positive charge is less than the distance from the center line. It is shorter by how much distance? Sir, it is shorter by this much of distance. And to find this much of distance, again drop a perpendicular. You will say this length is a by 2, this angle is theta. So this length is a by 2 cos theta. So this length comes out to be a by 2 cos theta. So the distance from the positive charge will be r minus a by 2 cos theta, as the distance of central line is r and this extra distance of central line is a by 2 cos theta. So you will say the distance from negative charge will be r plus a by 2 cos theta, while the distance from positive charge is r minus a by 2 cos theta. The net potential at this point will be nothing but the potential due to positive charge plus potential due to negative charge. So that will be equals to kq upon r minus a by 2 cos theta plus k into minus q upon r plus a by 2 cos theta. Now you can take kq common. You will be left with 1 upon r minus a by 2 cos theta minus 1 upon r plus a by 2 cos theta. You can cross multiply it. So here in numerator you will get r plus a by 2 cos theta. Here you will get r minus a by 2 cos theta, and in the denominator on multiplying r minus a by 2 cos theta and r plus a by 2 cos theta, you will get r square minus a square by 4 cos square theta. So when we do it, we get v equals to kq r plus a by 2 cos theta minus r minus a by 2 cos theta. When you open up the second bracket, this r get cancelled, this minus minus becomes positive, and you get a by 2 cos theta plus a by 2 cos theta, that becomes a cos theta. So you get v equals to kqa cos theta by r square minus a by 2 whole square cos square theta. This qa can be written as dipole moment, and we are solving for short dipoles. So a is less than r. So you can neglect this whole term in front of r square, and what you get is for a less than r, v equals to kp cos theta upon r square. You need to remember this formula. So if you have a dipole of dipole moment p, a short dipole, then at any distance r making an angle theta, the potential is given by kp cos theta by r square. The potential is given by kp cos theta by r square. You need to memorize this. Now, we know that the potential is kp cos theta by r square. Potential is a scalar quantity. We can even write this potential in vector format. How? See. We have got this dipole moment here. This distance of the point where we are writing potential is r. We know that potential equals to kp cos theta by r square. Think of it as kp r cos theta by r cube. Just have multiplied r in numerator and denominator, and you can write this p r cos theta as p dot r. So you can write potential to be k p vector dot r vector upon r cube. This is another way of writing the potential due to dipole. I have just multiplied r in numerator and denominator and written this p r cos theta as p dot r. So the potential at a point due to a dipole can be written as kp cos theta by r square or kp dot r by r cube. Me personally remember this particular thing, and I know how to convert from here to here. So let's move on and understand about potential more. If we have a negative charge and positive charge, they constitute a dipole. Think of the equatorial line. Each point on the equatorial line is at same distance from the positive and negative charge. Hence, at each point on the equatorial line, the potential will be 0, because the positive potential produced by the positive charge will be same as the negative potential produced by the negative charge. So at a point on the equatorial line, the potential is 0. At all points on the equatorial line, the potential is 0. For any point in front of the equatorial plane, any point here, all such points are closer to the positive charge and away from the negative charge. So at all such points, the potential will be positive. While all the points behind the equatorial plane, somewhere here. All such points will be closer to negative charge and away from positive charge. So here the magnitude of negative potential will be higher than the magnitude of positive potential. Hence the net potential at all such points will be negative. So at all the points in front of the equatorial plane, the potential will be positive, and all the points behind the equatorial plane, the potential will be negative. What you need to remember here is that on the equatorial plane, at any point, since each point is at same distance from negative and positive charge, at each point on the equatorial plane, the potential is zero. Hence, at any point on the equatorial line, the potential is zero. This is something you need to remember. Now let's talk about the most important thing we need to know about dipole. That is dipole in a uniform electric field. Let's say we have got a dipole. What is dipole? Pair of equal and opposite charge separated by some distance. And let's say here the charge has magnitude Q and the separation between the charge is A. If this dipole, the pair of equal and opposite charge, is placed in a uniform electric field E, we know that on the positive charge there will be a force in direction of field. How much? QE. On the negative charge there will be a force in direction opposite to the field. How much? The charge times the field strength E. Now if somebody asks you what is the net force on this dipole, so you will say on the positive charge there is a force QE towards right in the direction of field, while on the negative charge there is a force of same magnitude but in direction opposite to field. So the net force on the system of dipole is zero. And this is something important which is asked many a time. What is the net force on a dipole placed in a uniform field, a field of constant magnitude? So you will say the net force on a dipole placed in a uniform field is zero. And this result is independent of the angle made by the dipole moment vector with the direction of field. This result is independent of the choice of theta. So independent of the orientation of dipole, on the positive charge there will be a force in direction of field, on the negative charge there will be a force in direction opposite to field, and the net force will be zero. So the net force on a dipole placed in a uniform electric field is zero. Now how to write the torque? We have learned couple. The torque due to a couple is nothing but the force times the separation between the line of action of force. The magnitude of force here is QE, and the separation between the line of action of these two forces will be nothing but A sine theta. Visualize this triangle. So the hypotenuse is A. Here a force acts QE backwards. Here a force acts QE forward. And the separation between the line of action of these two forces is nothing but A sine theta. So the torque acting on this dipole due to the electric field is given by QE, the force times the separation between the line of action of force, which is A sine theta. You can club this Q and A and write the torque as PE sine theta. The dipole moment is charge times separation between the charges. Now we know that torque is a vector quantity, dipole moment is a vector quantity, and the electric field is also a vector quantity. So we can write the torque as the cross product of the dipole moment vector and the electric field vector. So in the vector format, we can write torque equals to P cross E. Independent of the value of theta, the force is zero. But the torque depends upon theta. For which value of theta, the torque will be zero. So you will say that the torque equals to Pe sine theta. The torque will be zero when sine theta will be zero, and sine theta will be zero for theta equals to 0 degree or theta equals to 180 degree. When I say that theta equals to 0 degree, it means that the dipole moment vector is in the direction of electric field vector. And when I say that theta is 180 degree, it means that the dipole moment vector is in the direction opposite to the electric field vector. We have learned that there is something called mechanical equilibrium. For a body to be in mechanical equilibrium, the net force should be zero and the net torque should be zero. The net force is always zero, irrespective of the orientation. But the net torque will be 0 when theta equals to 0 degree or theta equals to 180 degree. So you'll say for equilibrium, theta has to be 0 degree or theta has to be equals to 180 degree. When I say that theta is 0 degree, it means that the dipole moment is parallel to the electric field vector. When I say that theta is 180 degree, it means that dipole moment vector is opposite to the electric field vector. Now, we will say that the torque is maximum. The torque will have maximum value when sine theta will be maximum. The maximum possible value of sine theta is 1 when you take theta equals to pi by 2, or you say when theta equals to 90 degree. So the torque is maximum for theta equals to 90 degree, and this maximum value of torque will be when you substitute here theta as 90 degree. So you simply get PE into sine 90, and sine 90 becomes 1. So the maximum possible torque acting on a dipole in an electric field equals to PE. You get the maximum possible torque when the dipole is perpendicular to the field. So here we have learned multiple things. First thing, the net force acting on a dipole placed in a uniform field is 0. This result is independent of the orientation of the dipole. The torque acting on the dipole is given by P cross E. The torque will be 0 when the dipole will be parallel to the field, theta equals to 0, or when the dipole will be anti-parallel to the field, 180 degree. So the dipole will be in equilibrium in a uniform electric field when the dipole is parallel to the field or dipole is anti-parallel to the field. The maximum possible torque will act on the dipole when theta equals to 90 degree, and the value of this maximum possible torque will be nothing but the magnitude of dipole moment times the magnitude of electric field. Let's talk ahead. Let's understand something called potential energy of dipole in a field. Let's say we have got this dipole making an angle theta with the electric field E. We know that the infinitely small work done to rotate this dipole by an infinitely small angle d theta will be given by dw equals to tau dot d theta. Now we know that the torque is nothing but Pe sine theta. So the infinitely small work done has to be Pe sine theta d theta. Let's say we are turning the dipole from some initial orientation where it makes an angle theta 1 to some final orientation where it makes an angle theta 2. So we say the infinitely small work done by turning an infinitely small angle d theta is given by Pe sine theta d theta. To find the overall work done to rotate from orientation where the dipole moment vector makes angle theta 1 to the orientation where the dipole moment vector makes an angle theta 2, we will have to integrate. So the work done equals to integral Pe sine theta d theta from initial choice of angle theta 1 to the final choice of angle theta 2. Integration of sine theta d theta gives you minus cos theta. Lower limit theta 1, upper limit theta 2. Always substitute upper limit minus lower limit. So what you get work done is Pe into minus cos theta 2 minus of minus cos theta 1. Upper limit minus lower limit. So this minus minus becomes plus, and you get the work done to be equals to Pe into this minus minus becomes plus cos theta 1 minus cos theta 2. Once we have established this, we know what is the work done required in rotating a dipole. But our mission is not to find the work done. Our mission is to determine the potential energy of dipole in a uniform electric field. So we assume a reference potential. We say that let's assume that when theta equals to 90 degree, the potential energy is 0. So when the dipole is perpendicular to the electric field, let's assume that the potential energy is 0. We know that the change in potential energy equals to the work done by external agent, and that has to be equals to Pe into cos theta 1 minus cos theta 2. Now let's assume that the initial position theta 1 is 90 degree, for which we have assumed the potential energy to be 0 and theta 2 to be some random angle theta. So we will say taking theta 1 equals to 90 degree, for which we have assumed the potential energy to be 0 and theta 2 to be theta, and substituting the values, we get that the change in potential energy, which is potential energy final minus potential energy initial, but since we have taken initial potential energy as 0, we simply get the final potential energy. So the final potential energy for some orientation theta comes out to be equal to Pe into cos 90 minus cos theta. And we know that cos 90 becomes 0. So what we get is the potential energy when the dipole makes some angle theta with the direction of electric field is given by Pe into minus cos theta, which is minus Pe cos theta. And since P and E both are vector quantities and the angle between them is theta, you can even write this as the dot product. So rather than writing Pe cos theta, you can think of the potential energy to be minus P dot E, which is nothing but minus Pe cos theta. Now many a times students forget this minus sign. So beta, you need to keep this minus sign in mind. So the potential energy when the dipole makes some angle theta with the direction of electric field is given by minus Pe cos theta, which can be written as minus P dot E. Now let's utilize this to understand for what angle the potential energy will be maximum, for which angle it will be minimum, and what is the meaning of stable equilibrium and unstable equilibrium. So let's talk about stable and unstable equilibrium. Better remember one line. The universe craves for stability and stability is always attained at lower energy level. I taught you guys this UX graph while teaching you WPE, and I said that wherever you attain maximum potential energy, it's always unstable equilibrium, and the position for which you attain minimum potential energy, that is the position of stable equilibrium. Now we know that the potential energy is given by minus P dot E. Now tell me, potential energy is minus P dot E, which is equals to minus Pe cos theta. We have learned that the dipole will be in equilibrium for theta equals to 0 degree or for theta equals to 180 degree. If I substitute here cos 0 is 1. So for 0 degree, I get the potential energy to be minus Pe into cos 0 is 1, so I get minus Pe. And for theta equals to 180 degree, the other side of equilibrium, I get the potential energy to be minus Pe into cos 180, and cos 180 is minus 1, so I get minus Pe into minus 1, and minus minus becomes plus, so that becomes plus Pe. Tell me, for which orientation, for which choice of theta the potential energy is higher? So sir, for anti-parallel dipole moment, the potential energy is plus Pe. For parallel dipole, it is minus Pe. The universe craves for stability, and stability is always attained at lower energy level. The position for which potential energy will be minimum, that will be the position of stable equilibrium. So stable equilibrium is attained when theta is 0 degree. It means that the dipole is parallel to the electric field, and you get unstable equilibrium when theta is 180 degree. It means that the dipole is anti-parallel to the electric field. So for minimum value of U, for the minimum possible potential energy, theta should be equals to 0, and you get the minimum possible potential energy equals to minus Pe. This position for which the potential energy is minimum, theta equals to 0, when the dipole is parallel to the electric field, this position is called the position of stable equilibrium, and the dipole is in stable equilibrium. It has got minimum potential energy. For maximum value of potential energy, here when you use minus Pe cos theta should be minus 1. For cos theta to be minus 1, theta should be equals to 180 degree. When you take theta as 180 degree, the potential energy comes out to be minus Pe cos 180. Cos 180 is minus 1, so you get minus Pe into minus 1, that becomes plus Ee. So you say that the maximum possible potential energy is plus Pe, and the dipole has got maximum possible potential energy, so it is unstable. So it is in unstable equilibrium. So when the dipole is in the direction of field, the potential energy is minimum equals to minus Pe. When the dipole becomes anti-parallel to field, the potential energy is maximum equals to plus Pe. Keep this thing in mind. Remember that a freely suspended dipole always try to align itself in the direction of field. Why? Because when the dipole aligns in the direction of field, its potential energy becomes minimum, and the universe craves for stability. When we drop this marker, it falls down. Why? Because moving near the center of Earth, the potential energy of Earth pen system decreases. The universe craves for stability, and stability is always attained at lower energy level. So if you have a dipole placed at any goddammit orientation with the field, the dipole tries to turn and become parallel to the field. The dipole tries to turn and become parallel to the field. So remember that a freely suspended dipole tries to align itself in the direction of field. A freely suspended dipole always try to align itself in the direction of field. I will use this a lot when I will teach you about bar magnet. Here we are talking about electrical dipoles and electrical field. There we will talk about magnetic dipole and magnetic field. Either from here or from magnetism, a question will come in NEET for sure this year, where you will have to find the relationship of a dipole in a uniform field. This is a pet question. This is an FAQ, so you must know this properly. So now let's end this session with a question. Question is, determine the angle up to which a dipole should be turned from the position of stable equilibrium. It means that when it is parallel to the electric field, so that its potential energy is half the maximum. So by how much angle it should be turned so that its potential energy becomes half the maximum. Now students answer this question wrong many a time. That's why I have taken this particular example. By the way, whatever theory has been taught for dipole in uniform field, go through it twice so as to make sure that you know all the formula and all the theory about the questions coming from here are easy and scoring. So we know that the maximum possible potential energy is plus PE when theta equals to 180 degree. Now in the question they are asking the theta for which you have half the maximum potential energy. So you want potential energy to be half the maximum. So you want the potential energy to be PE by 2. And you know for any goddammit orientation, when the angle made by dipole moment with the field is theta, the potential energy is minus PE cos theta. Hence you need to find the value of theta for which the potential energy is half the maximum, that is PE by 2. So you will say U equals to minus PE cos theta, and you want this potential energy to be equals to PE by 2. Hence you want minus PE cos theta to be equals to PE by 2. Cancelling out PE both the side, you want cos theta to be minus half. For which value of theta cos theta is minus half? So sir, in the first quadrant cos theta is positive. So definitely here we are looking for an obtuse angle for which value of theta cos theta is minus half. So cos theta is minus half for theta equals to 120 degree, or 120 degree can also be written as 2 pi by 3. So theta has to be equals to 120 degree or can be written as 2 pi by 3. So that's all in this hour. In the next hour we will talk about the properties of conductors, and that will be really useful in the chapter of capacitor, which will be taught after current electricity. So see you guys in the next hour. This is all for this hour. Bye bye. So that's all for now. See you guys in the next hour.